at those two types of dating today. And the first one we're going to start with is absolute dating. Well, that just rolled in there, didn't it? Okay, a lot of times this is referred to as radiometric dating. And the reason is and we talked earlier about the chemistry with atoms. You have protons, electrons, and neutrons, right?
Yes.
Okay, so radiometric dating takes isotopes, which is the atom, it's a varying number of neutrons in an atom because we know that the protons identify the type of atom. It tells you what element it is. The electrons give you the charge of the atom, whether it's a positive or negative. And then the neutrons make it different isotopes by the varying neutrons. So, Patty? Take it away.
They're not the varying.
Pardon?
It's the decay of the protons, or it's gamma, beta, or isn't it the decay of the protons?
Yes,
Did you say the neutrons?
the neutrons is what makes it an isotope.
Yes.
But through sometimes, like in carbon, in the naturally occurring, we have carbon-14, we have carbon-13, and we have carbon-12. And when we breathe in, we're breathing in all three of those, right? So whenever that carbon is absorbed into our bodies, whenever we eat the plants, our bodies are absorbing that. So that ratio of 12 to 13 to 14 is in our flesh, it's in our bones, it's in everything. So let's say I died and y'all found me out in the pasture, my bones. And you said, oh, let's see how old this bone is. And so you took me to the lab and you're testing the ratio of carbon-12 to carbon-13 to carbon-14. And you do this because carbon-14 isn't a stable isotope. Carbon-12 and carbon-13 are. They stay there forever and ever. Amen. Carbon-14, though, is not stable. It breaks down into other
nitrogen.
stuff. Yes, so it loses a proton, what is it, 2 protons? So the atomic number comes down to nitrogen. So that's what we're going to look at today in the lab called pitching pennies. We're going to look at carbon decay, carbon-14 decay. Okay, so first of all, though, we're gonna look at another type of decay of uranium-238 to lead-206. Now, there's something called a half-life, and that's the time that it takes for half of that element, half of that radioactive element to break down or decay into the other element. It's the parent and the daughter. So the half-life is the time that it takes for half of it to break down. Some things have a very short half-life. Some of them have a really long half-life. You want to take over from here?
Yeah, and you're gonna.
I will click for you, yes.
We did not in this course teach chemistry, and I don't know exactly for sure when is the first peak that uses isotopes. Do you know? Does anybody here know? I know that by 8th grade they better understand isotopes, and so I'm not familiar with where.
In 8th grade, it's discussed. It's not tested.
Until or it is in.
It's tested in high school, but
Not in 8th grade, but you introduced. Okay. All right. So what happens in uranium-238 is it decays in 4.5 billion years. That's its half-life. That means half of what that animal had stored would change into lead, because that's what uranium-238 decays to. But it would take that long.
Wow.
So at the end of that much time, you would have only 50% of what was originally stored, okay? So they really are looking at the percentage of uranium-238 as opposed to lead. That's what's deciding how many half-lives that animal or that plant or rock has lived, okay? So obviously this isn't used today living material, right?
Okay.
And so you use something with a shorter half-life. And so technically, we really use mostly carbon because we're interested in fossils and we're interested in man. Archaeology, right, our past instead of Earth's past. Okay, so I'm just going to do this very briefly because radiometric dating is complicated, okay? All right, so she was talking about the nucleus changes. Do we have the graphic next? Got it, sorry. Okay, and so down here is the atomic number, and it tells you what about an atom?
The protons.
Number of protons. This is positive charges right here. This is the mass number. How much of the atom is included in a mass measurement? Protons and neutrons, just the nucleus. The electrons are negligible. They're so tiny that they don't make any difference. And as it happens, a proton and a neutron have approximately the same mass. That's because a neutron is made up of one proton and one electron that are attracted to one another. Okay? And so, two things happen. You can lose an alpha particle and you can lose a beta particle. And then there are things called gamma rays. All right? Okay, but that doesn't affect the mass. It doesn't affect what element you have. So if we start off with uranium-238, you can see that it loses an alpha particle first because its atomic number went down by 2. It went down from 92 down to 90. You agree?
Yes.
An alpha particle is defined as the loss of a helium nucleus. Helium is element number 2, and its mass is 4. So that means that a helium nucleus is 2 protons and 2 neutrons. So when it lost that helium nucleus, that's what caused it to change into thorium. But next, it loses a beta particle. We no longer have uranium-238. We have thorium. A beta particle is the loss of a neutron. I'm sorry, the loss of an electron from that neutron, which adds 1 proton. So do you see how its proton count went up? It went back to element number 92 because it gained. But its mass number stayed the same. When uranium lost a helium nucleus, its mass number went down by 4 units. 2 protons, 2 electrons. Okay? And so it proceeds through that, and it gets all the way to here in that 4.5, 4.6, whatever it was, billion years. Okay? And so, we didn't teach you this, and I don't know how much chemistry you've had. And so, just so that you understand that these are unstable, isotopes are unstable. They're going to undergo radioactive decay all on their own. They're not stable. And so, 50% of them over this measured period of time should make their change. Okay? And then, if you start out with 100, according to that, after 1 half-life period, if you had 100 atoms to begin with, you should have how many?
50.
50. And if another half-life goes by, you should have only 25. And another half-life goes by, you have 12 to 13. Okay? And theoretically, you can get down to that very last atom that can decay. Won't always happen in a perfect 1 period lifetime because it's a 50-50 chance at that point, that 1 would make it. So you're going to do a simulation of radioactive decay, okay? So if you will open your, I'm sorry.
I have one question. The radioactive decay is only going to happen after it's ingested or after it's inside you, or could you get it where it's already been decayed?
Oh, it's already been decaying, but if it's stored in your body, then it's measuring from that point forward because the record is contained in your bones for the most part that would be left as a or a piece of cloth, or a piece of paper, or wood, or something, it's left in there from the point that that living matter ingested it or took it into its body.
But then wouldn't we be tracing it back, we're tracing it back to the original point? How do we know that?
You're not tracing it back to only the original point that you made use of it, or that rock collected it.
Well, how do we know where, that's kind of, like, I'm seeing how we can get
You're
back to
saying-
the original point.
I think what I hear you saying is that, isn't it going to decay even if it's not in our bodies?
Right, so like
Yes.
when we get it,
Right.
it's already been decaying, so how do I know
When,
where
when,
to trace it back to, where to stop that?
so I think what you're asking is, let me try to address that.
Good.
The variations of those the ratios vary. But with the radiation of the sun coming in, and correct me if I'm wrong, that carbon-14 is being created, like becoming radioactive, so there's, even though it's decaying, there's more creation out in the atmosphere, so those ratios are still kept there. Yeah. So
Relatively
yes, it's
so.
decaying, but there's also more coming in to add to that number. But once you ingest it, you're done. It's not being created in an organism.
And my concern was dating it back, when do I know where to stop that backwards dating if it was already decaying before I got it? Like,
Right.
how do I know where that?
All you're gonna know is how long ago it was that material died, if it's a living material. You know how long ago the dinosaur died by measuring, by radiometrically dating it.
Because you know, you
That's your
always started
backbone.
out at 100%.
No,
But that's
I
what
mean-
I'm
You're
saying.
measuring the ratio, right?
Yes.
right,
Yeah, so the ratio is constant. Then they're measuring
right,
How far
the
away from-
deterioration of where
Of
the
that
ratio
ratio.
started.
yes,
Yeah.
thank you. Okay, and so you have a plastic box on your, oh, wait.
Let's talk about this real quick before we move on to that lab. So we talked about carbon 12, 13, and 14. And your body takes it in, your body doesn't distinguish between any of those. All plants, animals, everything uses the carbon in exactly the same way. It behaves chemically in the same way. The only thing that it does is that carbon 14 decays into nitrogen. That's it. And so the half-life of carbon 14 is almost about 5,800 years. So it's much, much less than the uranium-238. So while the uranium-238 would be great to measure ages of rocks, it's not so good at measuring the ages of bones or fossils. So that's why we use the carbon, because we're using a much shorter half-life, which provides limitations on its own, but then it gives us a much broader analysis tool for life. So we use young dating, so it's not good for old things. It has its limits. So teeth, bones, shells, anything that was made of carbon is a good target for carbon-14 dating.
As long as it's not over 50, what did you say its half-life was?
5,800 years. Yeah. So if you have something that's 1 million years old, then
Carbon 14.
it might have decayed all the way out, so it's useless
Right.
to try to measure. Okay, now we're gonna go to this pitching pennies investigation that's gonna look at radioactive decay. So you have on your table, it's a box, and it has some pennies and some little chips in it, like bingo chips. You also have a handout in 2 parts called Pitching Pennies Investigation. Ignore the first page and turn to the second page. So the stapled part is what I'm talking about now. The 3rd page was left off, and that's the observations table, so you don't need that right now. Do you have
I don't have the
Oh, okay.
Oh, we're gonna have to count all the.
On the bottle itself, do we have slides?
No, they don't slides.
Once you shake it, it's not gonna matter what it is. Are you sure it even matters? I think about, I thought about it. In my head, I thought if they were heads up or tails down, wouldn't matter.
All right, so in your investigation,
Yeah, it doesn't matter.
I want you to open up your box, and you have pennies and chips. Turn your pennies
Followed her.
Tails up.
tails up. Yeah, the instructions say that you have to make them tails up.
Leave them in the box, though, turn it.
Okay, leave them in the box. Everything stays in your box. Just try to get them all with the tails up.
Yeah, but then every time we're not gonna put it back. No, we're gonna take that. And then we'll shake it. So we're putting them on as heads and now? I mean, we're putting it on It's one of those ones that one of the, oh, never mind, I see the other one. It's nothing, I thought it was that renegade. Two. This is just for the teacher because they're ready. Kids' time is right, exactly what it is. I have a woman for that. If I hear you talking, you're wasting my time, and I'm gonna waste yours. She will say it's recycling once a week, so I said, oh, go look at the recycling bin, check if it's there. I don't have time for that, 160, no, I have 200 students. I lied, I had 160. We do
All right, guys, listen up. After your first task was to turn the tails up.
Oh, not even that referral. Absolutely insubordination.
Turn your tails
We're
up,
looking at models.
and you have your chips and your tails up pennies in the box, right?
Yes.
Okay. Now your next step is to shake your box for 30 seconds.
No, you work so
You
hard.
can count time. You don't have to use your phone as a timer. You're going to open the box, carefully remove all of the pennies that are heads up. Just the ones that are heads up. Don't turn anything else over from tails to heads. Just take out the ones that are heads up. These are your nitrogens now. Your carbon 14s have turned into heads up nitrogens.
So what is the half-life in this model?
5,730 years.
Well, what is representative of the half-life?
The shaking.
The shaking, 30 seconds of shaking.
Time that you should, is 30 seconds.
Excellent. You know how many of these pennies you wouldn't get back if you did this with middle school kids? Yeah. No, at our school it's serious. It's a rebound. No, our principal is awesome. Our principal will take it 30 minutes. And even the minor ones like that, they get 30 minutes after school.
All right, you got them all counted?
Tails up and